Welcome to the General Psychology lecture on judgmental heuristics. You're probably not watching this lecture until you finish the second exam. It's the first lecture post-exam, and I think I made a point of not giving you readings on this so it wouldn't overwhelm you, but it's probably a good idea that I didn't give you readings on this, because if you did the readings first, it would spoil some of the activities I'm going to do with you. But the gist of today's lecture is how people make snap judgments about all kinds of things in daily life, and that includes personality judgments of a friend, a roommate, or a person that you know pretty well. It includes how dangerous a particular activity is. It includes whether the meals at one restaurant are a better deal or are more delicious than the meals at another restaurant. So very often we have to judge magnitude, riskiness, amount, and when we do that on the fly, we often have to do it very quickly. And when we do that very quickly, we use something called heuristics, and I'll give you a definition of them in just a moment. All right. But before I do that, I'm going to share with you something called the paper folding problem. I borrowed this from a very clever guy named Scott Ploust, who wrote a little book about 2 decades ago now on judgmental heuristics. And notice what I have here, you can barely see, the room's kind of dark, is an ordinary sheet of paper. And I want you to do a thought problem with me. If you took an ordinary sheet of paper and you doubled it, so I took the sheet of paper, I just doubled it, and then you can see, I just double it again. And of course, I can double it again. If you double that sheet of paper, now you physically could not do this, it would be impossible. But if you double that sheet of paper 100 times, I'd like you to think about that without breaking out your calculator. I'd like you to estimate very quickly how thick that sheet of paper would be. Again, it's a hypothetical question. I think the old Brett's going to speak over me, so I'm going to move pretty quickly, because when I click, it's probably going to make that it's going to tend to make that audio click. I don't want that to happen, so make an estimate before I move on, and I'll probably have to pause to avoid that Brett talking over Brett. Make an estimate of how thick you think the sheet of paper would be and write it down. Don't say big or tiny or something like that. Give me something in units of measurement. All right, I apologize if there was a little glitch there. If I clicked ahead, a recording of me would have played ahead. The last time I gave this lecture was the very beginning of the coronavirus issue, and I inserted audio files in the lecture and just posted it as a PowerPoint file. In your case, I'm recording it using Screencast-O-Matic. So I'm going to give you some feedback about the answer you gave. I hope you gave an answer. I hope you took the activity seriously. I'm going to give you some feedback without even being there. So the first feedback I'll give you about the answer you just gave is going to come from, I think I'll pick Homer. And this is a recording, but Homer can give you feedback. Let's hear that again. Yeah, Homer says your answer is incorrect. In fact, in particular, he said your answer is too low. You need to offer a bigger answer. So if you don't mind taking that feedback, trust me, I could be wrong, but I'm pretty sure your answer is too low. I'd like you to make a bigger guess, a much bigger guess, and write that one down. And then Flanders will give you some feedback as well. If you're not a fan of The Simpsons, you don't know these characters, but you'll at least recognize what they have to say. So write down a much bigger guess than your first guess. Do it quickly. Remember, these are snap judgments, not calculus class. Write down a bigger answer than the one you just gave, and then Flanders will give you some feedback. Here we go.
Don't you kids know anything?
Yeah, Flanders is saying that your new guess, your adjusted guess, your second guess is still too low. So I'd like you to take that second guess and make it even bigger. In fact, make it much, much bigger, but make it concrete, write it down, and then Mr. Burns will give you some feedback. That's Mr. Burns here in the center, in case you're not a fan of The Simpsons. Write down a bigger number, a bigger amount, a bigger distance, and Mr. Burns will give you some feedback. Here we go. Yeah, that's Mr. Burns' evil way of saying dude or dude-ass person. You were way off base. Even on your third try, Your answer was way too low. If you want some feedback from Grandpa Abe, here's his feedback, by the way.
Love is a happy time all throughout the universe.
Yeah, I'm gonna have to quiet him. He just goes on forever. Yeah, he's a bit of a rambler. But notice he did mention the universe, and it's funny that he did because I never get to say what I'd like to say to people. I gave this problem at least a dozen years ago to my brother, the math teacher, and I did not get to say this to him. I did not get to say that his answer was no. And when I was given the problem myself for the first time, I did not get to pat myself on the back. I gave an answer like I bet you did that was way too small, and I'll prove it to you. At least I'll begin to prove it to you. If you're super careful, you may want to prove it to yourself. But we're going to advance to the next slide. I'm going to show you that's the answer. The answer is 2 times 2 times 2 times 2, 100 times. Of course, you double it 100 times. Then you multiply that amount, 2 to the 100th power, times 0.1 millimeters. And what annoyed me about my answer the first time I got the question is if I just thought a little bit more deeply, I could have come really close to the correct answer because I'm a bit of a math geek and I happen to know that 2 to the 10th power is 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So 2 to the 10th power is 1024. Check it out in your calculator if you didn't follow my quick math. And if we round that down generously to 1,000 and make the math really, really easy, that means 2 to the 20th power, I'm holding up two fingers, one for the 10th power, one for the 20th, is about 1,000 times 1,000. Now it's a bit more because it's 1,024, but to make the math really easy, we have 1,000 times 1,000, that's a million. 2 to the 30th power must be a billion. 2 to the 40th power must be a trillion, a quadrillion, quintillion, sextillion, septillion, octillion, nontillion. I might have been off in some of my prefixes, but it's a massive, massive number. And if you convert that number to something that's kind of meaningful to most people, the correct answer to the paper folding problem is about 850 trillion times the distance between the Earth and the Sun. That's called an astronomical unit. It's about 93 million miles times 850 trillion miles. In fact, it's almost the width of the known universe. It's just mind-bogglingly big, but very, very few people come up with an answer that big in their head because they think intuitively instead of thinking logically, mathematically, or rationally. All right. So yeah, almost the width of the known universe. The universe is about 14 billion miles. The single one universe that we can observe for sure. Multiverses, that's a different thing. Okay, so it's a massive number. Almost nobody gets to that massive number. Okay, that was math. Math is difficult, especially when you try to, multiply 1,024 times 1,024 times 1,024 in your head and keep going. This one, the activity I'm going to do with you now is much easier. And I'm going to play for you a series of names. Each name is going to appear, I just timed it, for exactly 2 seconds. At least there's going to be a screen for each name for exactly 2 seconds. I'd like you to pay very careful attention. Of course, you should not write anything down, but pay careful attention to this list of, I'll go ahead and tell you right now, this is going to be a list of 22 names that pop up for 2 seconds each. On your mark, get set, get ready to pay attention, go. Whoops, I told you to click go. Okay, that was it. I probably shouldn't have told you up front that there were 22 names, and I guess that's okay that I did. I'm going to give you about 15 seconds now. I won't use my timer. I'll just estimate. I'm going to give you 15 seconds to think about the names. All right, that was about 15 seconds. Now I have a pretty simple question for you. As I told you a couple of times, the list contained exactly 22 names. That's a fact. Go back and play the video back if you want to confirm that. I hope it felt like about 22 names. My simple question for you is, out of those 22 names, how many were male and how many were female? Of course, your answer should add up to 22. So quickly jot down the number of male names. This is your estimate, and the number of female names in the list. Make sure your answers add up to 22. But I'm just going to give you a few seconds. The only math you have to do is at making sure they add up to 22. And then you'll get to hear um, a younger version of me say something about that, I think. Let's see. Okay, you wrote it down. I'm trusting you wrote it down. The answer, I may have skipped ahead too quickly there, is that there were exactly 11 female and 11 male names. So I hope you wrote down something before I showed you that. I actually expected there was an audio recording here and I was going to click on it, but apparently I erased it. Yes, there were exactly 11 male and 11 female names, and I bet on the next slide I'll say so. Oh, there it is. There's it. Let's see what I had to say about that. Let's hear a younger version of me who wasn't out in the sun all day like I was say something about that. The two most common answers to this problem are that there were 12 or 13 female names, followed by 14 female names. And occasionally people will say that there were 11 male and 11 female names. People also will occasionally say that there were 15 or more female names. And it's very, very rare for people to make the incorrect estimate that there were more male than female names. And as you can see here, there was an identical number of male and female names, 11 of each. Most people remember there being more female names in the list because the female names in the list were substantially more likely to be famous. Beyonce, for example, is much more famous than Robert Dole, who ran for president a couple of decades ago. So almost all the female names who are famous are very famous, whereas only some of the male names were very famous. A good number of them were moderately famous, and quite a few of them were not famous at all. We'll get to the exact explanation for how that biased your memory later in this lecture. Yeah, let me just add, notice that a few of the male names were very famous, like George Clooney was in there. I think Justin Bieber was in there, but there were also people like Tim Howell, who was my friend in my high school track team, who was not famous at all because Tim was fast, but he wasn't that fast. He never made the Olympics. So there were a few famous male names, a few slightly famous names, and a handful of male names that weren't famous at all. But every single female name was moderately to very famous, which makes it easy to remember them. And if it's easy to remember them, you're going to think that there are more of them if you use something, I'm going to go ahead and say it right now, called the availability heuristic. But before we talk about that heuristic, let's talk about the general problems with making snap judgments. And let me just let you know that we often use heuristics when we make snap judgments. And I don't think I've given you a definition yet, but here it is. A judgmental heuristic is a simplifying strategy, a quick but imperfect, quick but dirty rule of thumb for making very rapid judgments. It's a rule that you use when you want to make a snap judgment when you don't have much time. We're just going to look at 3 of them. Depending on how you count, there are 5 or 6 or 8 of them. There's at least a handful of them. We're just going to cover 3 to give you a sense of what they're like. And then we're going to talk about how good we are at correcting our initial judgments. And we're going to talk about phenomena like overconfidence, for example. All right, so let's look at 3 very carefully studied judgmental heuristics. Each of these is used to judge magnitude or amount most often. There are other heuristics we use for other things, but the three judgmental heuristics I'm going to use or I'm going to review for you are the ones that help us judge how likely, how frequent, how dangerous, that sort of thing. And one heuristic that we use that in fact you just used, and I couldn't resist saying it about a minute ago, is the availability heuristic. You judge the frequency of an event, the number of female names on the list versus the number of male names on the list based on how easy it is to recall the event. So if you can think of a lot of events, you think, well, that's happened a lot, that category's happened a lot. But if you can't, you think, well, I guess it hasn't happened a lot. So quick example, if you think more Americans have horses as pets or have horses on the farm that they live on than have llamas as a pet or as a grazing animal on a farm, you are certainly correct, right? Because horses are way more frequent. You've seen more horses driving through country roads than you've seen llamas. And if you think that people are more likely to get killed in car accidents than to get killed while deep sea diving, you're almost certainly correct because not many people go deep sea diving. So that's the availability heuristic. Usually it's pretty useful, but it can lead us astray. And I'm going to let you think about these four causes of death and ask you to pick one in each pair that you think is the more common cause of death. And I'll just let you do that first, and I'll have a more specific question. So from each of those pairs, some of these are very easy, some of them are quite difficult. Choose the more common way that people die. All right, I'm going to ask you to do it quickly because these are snap judgments, not calculations. Don't Google it. Just trust your gut on each one, and then we'll talk about your gut. And even if you made a correction to your gut answer, you might think about what most people might say. All right, I'm going to assume that you had a chance to do that very quickly. You picked either smoking or plane crashes. You picked either cancer or heart disease. You picked either suicide or homicide. I'm going to assume that you did that. But then I'll ask you in the example of question one, almost everybody gets that one right. Most people recognize that more Americans die every year of smoking-related illnesses, like lung cancer, for example, than of plane crashes. Almost nobody thinks that plane crashes kill more people than smoking. But the question becomes a bit more difficult if you ask people, well, exactly how many more? Like, what's the ratio? For every person who dies in a plane crash in America in a given year, and it does vary year by year, of course, but on average, how many people die on average of smoking related illnesses? So the answer is, of course, more people die of smoking. How many more people? 10 times as many, a billion, 850, not 850 trillion times as many. Exactly what's the ratio? For every person who dies in a plane crash in the US in a given year, about how many people die of smoking related illnesses? All right, the answer to that question, I looked up a few minutes ago, the exact number, at least for plane crashes. It varies a lot year by year. In 2018, it was a bit more than 500. I think it was 534, something like that. But in 2019, it was only something like 253. So it's several hundred people per year in all kinds of plane crashes. But of course, way more people die of smoking related illnesses. What most people don't recognize is that it's many hundreds of times more. Depending on which expert you trust, the approximate number of people who die every day, not every year, of smoking related illnesses is something like a couple of jumbo jets crashing. It's 500, 600, 800, depending on how generous your definition of a smoking related illness is. But every day, several hundred Americans, no doubt 500, 600, die of smoking related illnesses. That's way, way more common than plane crashes. But people are often overly fearful of plane crashes and not fearful enough of smoking, because plane crashes, of course, get media attention. So we're going to zip through these other ones pretty quickly. And I'm probably going to start talking. If I do, I think I can shut myself up. We're going to circle the most common one there. The most common one there is heart disease, not by a dramatic gap, but heart disease kills more people than cancer. You probably hear more about cancer, so people think cancer kills more people. Many people think that more Americans die every year of homicide than suicide. It's pretty darn close, but on average, it's suicide more common. And most people guess that diabetes kills at least a little bit more people than Alzheimer's, but the reverse is actually the case. You hear more about diabetes in the media than you hear about Alzheimer's, but Alzheimer's is growing even more rapidly than diabetes, by the way. Okay, one more quick example. If you ask most people if crime rates in America are going up or going down, people pretty consistently report almost any time you ask them, 1950s, 1980s, 2010 today, most people think that crime rates are and have been on the increase. But in fact, in the past couple of decades, they've been pretty dramatically on the decrease. But we think that crime rates are increasing because we pay attention to crime rates in the media, and they get a lot of attention. So when I used to work at Gallup, which is a news agency as well as a polling agency, they sort of sarcastically made fun of some other news agencies for only covering disasters. And when they did that, they said, if it bleeds, it leads. So if there's an explosion, if there's blood, if there's death, that's going to be a front page story. And they prided themselves on not taking that approach. Okay, so that is the availability heuristic. The next heuristic I'll talk about with you, in fact, I'll probably get my less exhausted, less dehydrated self to talk about a little bit, is the representativeness heuristic. That is a mouthful. I like to call it the similarity heuristic, but I can't get anybody else to do that. So the name that's stuck, been around for more than well over 40 years now, is the representativeness heuristic, but it means similarity. This happens when you judge the likelihood of an event based on how well it represents or is similar to some other event or some category of events. So for example, when I was a kid, my mother told me not to play with frogs because she was positive that they cause warts. A likely basis of that belief, of course, is that frogs look like they have warts. They don't have warts, but they're bumpy. And so they look like they have warts. And many people concluded that they cause warts, so they don't. Okay, so to get to something that's a bit more familiar to you, I'm guessing, because you probably don't catch frogs as a little kid anymore. If you ask people which of those series of coin tosses, H, 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 those are 5 heads in a row, or H, T, H, H, T, many people quickly report that the second is more likely. But if you stop and do the math, and you do the quick calculations even, it's 1 in 2, 1 in 4, 1 in 8, 1 in 16, 1 in 32. Each of those exact sequences will happen exactly 1 time in 32, because it's 1 in 2 times 1 in 2 times 1 in 2 times 1 in 2 times 1 in 2. That is 1 in 2, 4, 8, 64. They're both pretty unlikely. Any particular sequence is pretty unlikely if you flip a coin 5 times. But the second category represents or is similar to a random sequence. It resembles it more, so people think it's more likely, right? If you have friends who play the lotteries, and I have some family members who play the lottery, I've practically never played the lottery because the odds on it are terrible. I've gotten a few lottery tickets as holiday gifts before, by the way, but otherwise, I don't know if I've ever bought a lottery ticket, but if I have, it's very, very rare. If someone were to give you a lottery ticket for a big lottery like Powerball or something, imagine you could choose between the ticket on the left, you get the big prize if it's 3, 11, 14, 20, 25, and 47, or you get the big prize if the winning numbers are 1, 2, 3, 4, 5, 6 out of those 50 or 60 numbers. Very few people say they would pick the second category. I say I would. I'll explain to you why. First of all, the reason people prefer the first sequence over the second sequence is the same heuristic. That series on the left looks random. It looks arbitrary. It looks like it could be a winning lottery ticket. It could, but the chances are one in many hundreds of millions because it's so hard to win the lottery. It is no harder at all to win the lottery with 1, 2, 3, 4, 5, 6. It's just that both of them are very, 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 very unlikely. The odds are 1 in, let's say there are 50 numbers, 1 in 50 times 1 in 49 times 1 in 48 times 1 in 47 times 1 in 46 times 1 in 45. And that is a very small number. The reason I would pick the second set, by the way, is that I know that nobody else would be likely to pick it. So in either case, I'm very, 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 very unlikely to win. But at least if I win in that second case, there's almost no chance anybody else also won it and that I have to split the big prize with them. In the case of the first prize, it's more likely, even though it's rare, that somebody else also picked that sequence. Maybe they picked it because their birthday is March 11th. Their wife's birthday or their boyfriend's birthday is the 14th. Their high school jersey number was 20. They live at 25 Elm Road, and their mother is 47 years old. You know, some weird set of quirky coincidences like that might make them buy that ticket. Very few people are going to buy 1, 2, 3, 4, 5, 6. So if they're free, that's the one that I'll take. Okay. One more quick example of this is Frank and Gilovich's classic black jersey studies. They published a paper in 1988, I think it was, both in FL and NHL. They got like 20 years of records in both sports, all the records they could get at the time. They kept very careful records, or took very careful records for, again, something like 18 years in both sports, for exactly how many times teams got called for penalties in football and in hockey. And they made the assumption that because the color black is representative of or reminds people of aggression, that referees would be biased by this exact heuristic and would judge the behavior of a person on the football field or on the hockey in the hockey rink on the ice to be more aggressive if they were wearing a black jersey. And that's exactly what their studies showed. On top of those field studies, they did multiple experiments, and those experiments showed the same thing. So if you put people in black t-shirts versus white t-shirts while they play a pretty aggressive game, the people in the black t-shirts are perceived to be more aggressive than the people in the white t-shirts. As a matter of fact, if you put people in the black versus white t-shirts, you see that people actually behave more aggressively when wearing the black t-shirts, but people perceive them as even more aggressive than they are. So they've looked at this in quite a bit of detail, and they argue that through something like the representativeness heuristic, even professional referees, who are pretty good judges, by the way, these people get paid because they're good. Okay, even professional judges are biased by the fact that the color black is thought to be representative of aggression. Okay.
In what way did
I'm going to keep moving there. So availability and representativeness are specific heuristics. I'm going to share one more with you. Another heuristic I'm going to share with you has to do with counting rather than comparing or remembering. And that heuristic is the numerosity heuristic. It's judging how much of something there is, the magnitude of something, based on the number of pieces into which it's divided. It's basically counting and using a head count, a count of the number of apples somebody has to make an apple pie, to conclude how much of something you have, or how probable or how likely something is. So one of my favorite examples, if I can get this to work, is from Nigel of Spinal Tap. Well, I'm going to pause it.
This is a top to a,
All right, here we go. It's very hard to get that to play.
Very special because if you can see,
back it up here because I spoke over him.
This is a top to a, what we use on stage, but it's very, very special because if you can see, the numbers all go to 11. Look, right across the board.
Right, across the board.
11,
and most of the
11, and then
amps go up to 10.
Exactly.
Does that mean it's louder? Is it any louder?
Well, it's one louder, isn't it? It's not 10. You see, most blokes, be playing at 10. You're on 10 here, all the way up, all the way up, all the way up. You're on 10 on your guitar. Where can you go from there? Where?
I don't know.
Nowhere, exactly. What we do is if we need that extra push over the cliff, you know what we do?
Put it up to 11.
11, exactly. One louder.
Why don't you just make 10 louder and make 10 be the top number and make that a little louder?
These go to 11.
Right. So the point of that little video is that Nigel is not. Whoops! Let me pause that. Let me pause that. Let me pause that. Okay, we're back. Sorry, that's always difficult to get that particular clip to play. But the point that I was making by selecting that clip is that Nigel's probably not the sharpest tool in the shed. And if you ask him if it's any louder, just because it's numbered to 11, his answer is that it's one louder now, isn't it? Well, what's one? If it's not a meaningful unit of volume, like decibels, then it's not really any louder. But it feels louder to him because there are 11 of them. All right, so that's that. If you're a fan of Chipotle, when they started opening at 11 about a couple of years ago, they did a spoof of that joke and said, this one goes to 11 because they started staying open until 11. I don't know if they still do, but in that case, they really were open an extra hour, and that was good if you're a fan of Chipotle. But just making the numbers go to 11 doesn't guarantee that there's really more volume, more of something to listen to. Okay, so that's that. Let's see if we can keep moving here. One of my favorite examples, and this example annoys people, especially if they're swimmers, is Michael Phelps. There was a long window when people claimed that Michael Phelps was the greatest athlete of all time. Eventually they backed off on that and just claimed that he's the greatest Olympian of all time. But I hope you can see how at least it's pretty reasonable to conceive of that judgment, because there have been a lot of amazing Olympians, and he's just one of them. To conceive of that bias to think he is even more awesome than he is. He's obviously an amazing swimmer. Nobody doubts that. Whether he's the greatest Olympian of all time, that's a much, much, much more difficult question. And I personally don't think he is. It is the case, though, that in the 2016 Olympics, and I don't know if he's going to swim in the 2021 Olympics when I hope they come to Tokyo about a year late, he won his 28th 2/8 swimming medal. That is amazing. No one's ever come close to that. And of course, many people concluded from that that he's the greatest Olympic athlete ever because nobody else has come close to that medal account. I think that reflects a numerosity heuristic. I'm going to break it down for you very quickly. I can go forever on this one because I love track and field. And by the way, I'm a terrible swimmer, so maybe I'm a bit biased against swimming. But my daughter is a swimmer and she loves swimming. So that at least makes me have some appreciation of swimming, I hope. But I don't think that we can say because Michael Phelps has 28 medals, most of them gold, that guarantees that he's better, for example, than Usain Bolt. First of all, Michael Phelps is only competing against that relatively small portion of people on planet Earth who are rich enough to live in countries that have access to swimming pools, in fact, have them year round. So Michael Phelps swims in January. He at least used to live in Baltimore, so wherever he lives, he can swim in January, February, December, even though it's freezing cold outside, because he lives in a wealthy nation. And even growing up, he had to be reasonably wealthy. So Michael Phelps is competing against all the rich nations on the planet. Usain Bolt was competing against everybody. Every place on earth people run, and people who run fast are recognized for that. Okay. As it turns out, there are 4 different swimming strokes, 4 different ways to swim. There's the backstroke, the butterfly, there's the freestyle. What am I forgetting? Backstroke, butterfly, breaststroke, and the freestyle. There are 4 different ways to swim, and almost anybody who's good at one is at least pretty good at the other. Michael Phelps swims at least some of those strokes some of the time. In fact, one of the things that he swims is the individual medley relay, where he himself swims one lap or one, let's say 100 meters with each of those 4 different strokes. From my perspective, there should be 1 stroke in swimming, probably the freestyle because it's the fastest. We don't need to have 4 different swim strokes. It quadruples the number of swimming medals that people can get in the Olympics. Okay, so I'm putting another picture Usain there. And of course, I forgot why I sort of mentioned that swimming also has many, many, many relays. Track and field only has 2 in the Olympics. Swimming has many more. I could go on and on about the fact that swimming is a low impact sport. People don't get knee injuries in swimming nearly as often. You can still be 40 years of age and be a very good swimmer. It's impossible to be 40 years of age and be a truly world-class sprinter. Your body just isn't that quick anymore. So for all these reasons, it's not a fair comparison. So I would argue, difficult argument to make that Usain Bolt is probably an even greater athlete than Michael Phelps, or at least I would say we can't say who's greater because we're comparing apples and oranges. Okay. Now it's time for me to make briefly my joke about why there are 4 swimming strokes and so many swimming medals in the first place. And I honestly think there's a sociological, anthropological, social, psychological reason. The reason there's so many ways to win swimming medals is that white people appear to be pretty good at it. When rich people are good at something, they like to get those medals. So it is no accident that a bunch of rich white Europeans and Americans got the Olympics going in 1896 or back whenever it was, and pretty quickly they started filling it up with all kinds of swimming races. At first there weren't many, but they grew and grew and grew. All right, that's that. Okay. I hope it's pretty clear to you by now then that Kellogg's uses or tries to use the numerosity heuristic to get you to think that Kellogg's Raisin Bran is absolutely packed with raisins. Okay, and the answer here is a clue. They say, I guess, unlike other brands of Raisin Bran, that there are 2 scoops of raisins. Well, that's kind of like saying there are 2 screwdrivers or 2 hammers. A scoop is not a unit of measurement. A scoop is a tool for grabbing stuff and moving it from one box or container to the next. There's absolutely no standard size for a scoop. So you could say there are 8,000 microscopic scoops of raisins in a box of Kellogg's Raisin Bran, and you would be technically correct. So that's a laughable example, I think, of the numerosity heuristic. There are lots and lots of other examples. We're going to keep moving here. We're going to come to the general conclusion that we often judge frequency or amount. We judge frequency, amount, or likelihood using judgmental heuristics like the ones I just mentioned. The short answer to why, and we're going to delve into this more deeply later, is that heuristics are adaptive in general. They work reasonably well, and if they didn't, we wouldn't use them. A much more technical answer that we'll get to not until a couple of lectures down the road is that heuristics are automatic, but using more sophisticated decision rules is controlled. In the interest of time, I'm going to be very brief and I'm going to stop right there. In fact, what I think I'm going to do is pause this lecture here. I'll pick up and give you another short lecture on how good we are at adjusting our judgments and at how good we are at knowing whether we're likely to be correct or not. So I'm going to say goodbye right here, just briefly, and we're going to take a pause, and I'll pick up and have lecture B on judgmental heuristics a little bit later. Talk to you soon.